In the pristine halls of the Mauna Kea Observatory, astronomer Dr. Yuki Tanaka stands before a holographic display that has haunted her dreams for months. The three-dimensional map floating before her shows the local cosmic neighborhood in unprecedented detail. Every galaxy, every star cluster, every wisp of intergalactic gas mapped with precision that would have been impossible just a decade ago. But what should be a triumph of astronomical mapping has instead revealed something deeply unsettling. The space around us, for billions of light years in every direction, is littered with the remnants of cosmic structures that no longer exist. Ghost galaxies whose stars have long since burned out, the skeletal remains of galaxy clusters torn apart by dark forces, and vast regions of space that bear the chemical signatures of stellar explosions from civilizations that vanished before our solar system, was even a glimmer in a molecular cloud. We are not, as we once believed, residents of a vibrant cosmic neighborhood. We are archaeologists living in a vast cemetery, surrounded by the fossilized remains of a universe that was once far more alive, far more populated, and far more magnificent than the sparse cosmos we observe today. This macabre revelation forces us to confront one of the most disturbing questions about our place in cosmic history. Are we late arrivals to a universe that has already experienced its golden age, leaving us to wander among the graves of cosmic civilizations we will never know? To understand the scope of this cosmic cemetery, we must journey back to the universe's youth, when the conditions for galactic life were radically different from anything we observe today. Roughly 12 billion years ago, when the cosmos was less than 2 billion years old, the average density of matter was over 1,000 times higher than it is now. Galaxies existed in close proximity, their gravitational influences overlapping in complex networks that fostered constant interaction, merger, and exchange of material. This was an epoch of cosmic fertility, unlike anything we can imagine. The Hubble Space Telescope's deep-field observations have captured glimpses of this ancient abundance images of the distant universe, revealing galaxy densities so high that the space between them was measured not in millions of light years, but in mere hundreds of thousands. These primordial galaxies appeared as brilliant blue beacons, their spectra dominated by the light of massive young stars burning through their nuclear fuel at prodigious rates. But the story these ancient images tell is one of gradual loss rather than growth. As astronomers push their observations deeper into cosmic history, they discover that the universe's peak epoch of galaxy formation occurred roughly 10 billion years ago. Since that time, the rate of new galaxy formation has declined precipitously, while the rate of galactic death has steadily increased. We are living in an era where more galaxies are dying than being born, a cosmic demographic transition from growth to decline. The evidence for this galactic mortality crisis comes from multiple sources. The Sloan Digital Sky Survey, the most comprehensive census of nearby galaxies ever conducted, reveals a universe dominated by red and dead, elliptical systems galaxies that have exhausted their star-forming gas and entered a phase of senescence characterized by aging stellar populations and minimal new activity. These cosmic senior citizens far outnumber the vibrant, star-forming spirals that capture most public attention. Dr. Kate Whitaker's groundbreaking research at the University of Massachusetts has documented this transition in exquisite detail. By studying the colors and spectra of thousands of galaxies at different cosmic epochs, her team has mapped the process by which active, star-forming systems transform into passive, aging graveyards. The transformation appears to be accelerating. Galaxies are quenching their star formation at increasingly rapid rates, suggesting that some fundamental change in cosmic conditions is making it harder for galaxies to maintain their vitality. The mechanism driving this galactic death appears to be related to the mysterious process astronomers call feedback, the way that stars and black holes inject energy into their surroundings, heating gas and preventing it from cooling and condensing to form new stars. In the early universe, when gas densities were high and feedback processes were still developing, galaxies could easily replace any gas that was heated and expelled. But as cosmic expansion diluted the intergalactic medium and feedback processes became more efficient, galaxies began losing the ability to replenish their star-forming reservoirs. Computer simulations run on the world's most powerful supercomputers have revealed the brutal efficiency of this cosmic sterilization process. The Illustris and Eagle simulation projects, which follow the evolution of thousands of galaxies across cosmic time, show how stellar winds, supernova explosions, and black hole outflows can completely strip a galaxy of its life-giving gas in just a few 100 million years. Once this gas is removed, the galaxy enters an irreversible death spiral, its remaining stars aging and dying without replacement. But the cosmic graveyard extends beyond individual galaxies to entire clusters and superclusters, the largest gravitationally bound structures in the universe. The Planck satellite's all-sky survey of galaxy clusters has revealed that many of these massive systems show signs of disruption and decay. Clusters that should be growing through the accretion of smaller groups are instead being torn apart by the accelerating expansion of space, their member galaxies scattered like cosmic debris across ever-increasing distances. The fate of the Virgo cluster, our nearest massive galaxy cluster, provides a sobering preview of this cosmic dissolution. Located roughly 50 million light-years from the Milky Way, Virgo contains over 2,000 galaxies bound together by gravity. But detailed studies of the cluster's dynamics reveal that it's already beginning to come apart. The outer regions are being stretched by cosmic expansion, while the central regions are contracting and heating up as smaller galaxies spiral into the cluster's massive central galaxy, MADI 7. This process of cluster cannibalism represents another form of cosmic death, the gradual merger and consumption of smaller systems by larger ones, until only a few massive, isolated galaxies remain. The end result is a universe populated by cosmic zombies, enormous elliptical galaxies that have consumed all their neighbors and now drift alone through the expanding void, their stellar populations aging and dying without hope of renewal. The James Webb Space Telescope's infrared vision has begun to reveal the full extent of this cosmic mortality. Its observations of distant galaxy clusters show that the process of galactic death was already well underway when the universe was less than half its current age. Many of the galaxies that appear bright and active in visible light turn out to be cosmic phantoms when observed in infrared. Their star formation has already ceased, and they're coasting on the momentum of previous generations of stellar activity. Perhaps most disturbing are JWST's discoveries of what astronomers are calling fossil groups, regions of space that once contained rich galaxy clusters, but now show only a single massive elliptical galaxy, surrounded by the faint remnants of its former companions. These cosmic crime scenes represent the end state of cluster evolution, where gravitational cannibalism has reduced a once thriving galactic community to a single survivor floating in a sea of stellar debris. The chemical archaeology of these cosmic graveyards tells an even more disturbing story. When galaxies die, they don't simply disappear. They leave behind chemical fingerprints that persist for billions of years. The European Southern Observatory's Very Large Telescope has detected these chemical fossils in the diffuse gas that fills intergalactic space. Clouds of oxygen, carbon, and silicon drift through the cosmic void, the only remaining evidence of stars that lived and died in galaxies that no longer exist. Dr. Jason Tumlinson's work with the Hubble Space Telescope has mapped these intergalactic graveyards in unprecedented detail. By using distant quasars as cosmic flashlights, his team can detect trace amounts of heavy elements in gas clouds located hundreds of millions of light-years from the nearest living galaxy. These orphaned metals represent the scattered ashes of cosmic civilizations, stellar systems that may have harbored planets, life, and perhaps even intelligence before being dispersed into the void by galactic death processes. The scale of this cosmic mortality becomes even more apparent when we consider dark matter, that mysterious substance that comprises roughly 85% of all matter in the universe. While we cannot observe dark matter directly, its gravitational effects reveal the skeletal structure of cosmic evolution. Computer simulations show that dark matter forms a cosmic web of filaments connecting galaxies and galaxy clusters. But these same simulations reveal that most of the dark matter structures that formed in the early universe have since been disrupted and destroyed. The Millennium simulation and its successors track the fate of millions of dark matter, halos, the gravitational scaffolding upon which galaxies form. The results are sobering. For every dark matter halo that survives to the present day, dozens have been torn apart by gravitational interactions, their materials scattered throughout the cosmic web. We live in a universe where most of the structures that once existed have been reduced to cosmic debris. This dark matter archaeology reveals another disturbing aspect of cosmic death, the loss of information about cosmic history. When dark matter structures are disrupted, they carry with them the record of how and when they formed. The destruction of these cosmic fossils represents a kind of universal amnesia, where the universe gradually loses memory of its own, passed through the inexorable process of gravitational evolution. The local group of galaxies, our immediate cosmic neighborhood, provides a microcosm of this larger pattern of death and disruption. What we observe today as a small collection of galaxies, the Milky Way, Andromeda, and roughly 50 smaller companions, is actually the remnant of a much larger structure that has been whittled down by billions of years of gravitational evolution. The Gaia Space Telescope's exquisite measurements of stellar motions within our galaxy have revealed the fossilized remains of dozens of smaller galaxies that were consumed by the Milky Way over its history. These stellar streams, long arcs of stars with similar compositions and motions, represent the stretched-out corpses of dwarf galaxies that once orbited independently, but were eventually torn apart by tidal forces. But even more disturbing is what Gaia's data suggests about the future. The ongoing collision between the Milky Way and Andromeda, predicted to occur in roughly 4 billion years, will be just the latest episode in a cosmic consolidation process that has been reducing the number of galaxies in our neighborhood for billions of years. After the merger, the resulting galaxy, already nicknamed Milkomeda, will likely consume the remaining dwarf galaxies in the local group, leaving a single, isolated system floating in an increasingly empty cosmic void. This process of cosmic consolidation appears to be accelerating due to the mysterious dark energy that drives the universe's expansion. As space itself expands at an ever-increasing rate, galaxies beyond our immediate neighborhood are being carried away faster than light can travel between them. This creates an effective cosmic horizon, beyond which galaxies become causally disconnected, unable to influence each other gravitationally or exchange matter through any known physical process. The Atacama Large Millimeter Array has detected the early stages of this cosmic isolation by observing the tenuous streams of gas that connect galaxies within the cosmic web. These intergalactic filaments, which once served as highways for matter exchange between galaxies, are being stretched and diluted by cosmic expansion until they can no longer sustain the flows that once nourished galactic ecosystems. Advanced computer simulations of future cosmic evolution paint an increasingly lonely picture. The Dark Energy Survey and other observational programs have provided the data needed to project cosmic evolution billions of years into the future. These models show that the accelerating expansion of space will eventually separate all but the most tightly bound galactic groups, creating a universe of isolated island universes, with no possibility of interaction or communication. Within these isolated groups, the process of galactic death will continue until only a single massive galaxy remains in each group. These cosmic survivors will then face their own inevitable demise as their stellar populations age and die without replacement. The last star's long-lived red dwarfs with lifetimes measured in trillions of years will eventually exhaust their nuclear fuel, leaving behind a universe of cold, dead stellar remnants floating in an ever-expanding void. The implications for life and consciousness in this cosmic graveyard are profound. If we are indeed living among the remains of a far more vibrant cosmic past, then the conditions that allowed complexity and life to emerge may have been much more common in earlier epochs than they are today. The rare combination of circumstances that led to our existence, a stable star, a rocky planet at the right distance, billions of years of relatively peaceful cosmic evolution, may have been the norm rather than the exception in the universe's youth. This perspective transforms the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of contact with alien civilizations, from a puzzle into a tragedy. Perhaps we are not alone because life is rare, but because we are among the last rather than the first intelligent species to emerge in our cosmic neighborhood. The civilizations that might have preceded us lived and died in galaxies that no longer exist, their achievements scattered to the cosmic wind, along with the stars that once warmed their worlds. The search for extraterrestrial intelligence takes on new poignancy in this context. Every radio signal we detect, every potentially habitable exoplanet we discover, every possible sign of cosmic engineering we observe might represent not the beginning of galactic civilization, but its end, the final gasps of intelligence in a universe that is rapidly becoming too sparse and energy-poor to sustain complex life. Recent discoveries of potentially artificial signals from space take on new meaning when viewed through this cosmic archaeological lens. The mysterious fast radio bursts detected by radio telescopes around the world might not be communications from active civilizations, but automated beacons left behind by species that knew their galactic neighborhoods were dying. These signals might be cosmic obituaries, final messages from civilizations that recognized they were living in a universe's twilight years. The study of exoplanets reveals additional evidence for cosmic death on galactic scales. The Kepler Space Telescope and its successors have discovered thousands of worlds orbiting other stars, but the statistics are troubling. The vast majority of potentially habitable planets orbit stars that are far older than our Sun, ancient red dwarfs that formed when the universe was young, and star formation rates were much higher than they are today. This age distribution suggests that most of the universe's potentially life-bearing worlds reached their peak habitability billions of years ago, during the epoch when galaxy formation was at its height, and cosmic conditions were far more conducive to the emergence and persistence of complex life. We may be living not just in a cosmic graveyard, but in a biological one as well, a universe where most of the life that will ever exist has already come and gone. The philosophical implications of living in a cosmic graveyard extend beyond questions of life and intelligence to fundamental issues of meaning and purpose. If the universe has already passed through its most creative and vibrant phase, then everything we observe today might be understood as an extended epilogue to a far grander cosmic story that we arrived too late to witness. Yet there is also a profound beauty in our role as cosmic archaeologists. Through our telescopes and detectors, through our theories and simulations, we are recovering the lost history of a universe that once teemed with galactic life, but has now entered its senescent phase. Every observation becomes an act of cosmic memory, preserving the record of structures and processes that would otherwise be forgotten, as the universe continues its inexorable slide toward increasing isolation and entropy. Standing in that observatory, surrounded by the holographic ghosts of dead galaxies, Dr. Tanaka realizes that her mapping project has become something far more significant than a simple astronomical survey. She is creating a memorial to the cosmic dead, a record of all the galactic civilizations, stellar communities, and dark matter structures that once filled the universe with activity and interaction, but now exist only as fading chemical signatures in the growing void. The universe may be a graveyard, but it is also a library, a vast repository of information about cosmic processes and evolutionary pathways that operated on scales we can barely comprehend. Every dead galaxy we observe, every disrupted cluster we map, every orphaned metal cloud we detect tells part of a story about how complexity and organization can emerge from chaos, flourish for a time, and then be swept away by forces beyond any individual system's control. In our brief moment as conscious observers, we have the privilege and responsibility of reading these cosmic tombstones, deciphering the epitaphs written in starlight and gravitational waves. We may be living among the dead, but we are also serving as witnesses to their former glory, ensuring that the universe's most creative epoch will not be entirely forgotten, even as the cosmos itself drifts toward a cold and lonely future. Perhaps this is the deepest meaning of our existence in a cosmic graveyard. not to mourn what has been lost, but to celebrate what once was, and to ensure that the memory of cosmic abundance persists even in an era of cosmic scarcity. We are the universe's way of remembering itself, preserving the story of galactic life and death in the brief interval before we too become part of the cosmic cemetery we are still learning to understand.